Today I'll be presenting to you two sessions. The first session will be on quantum optimization methods and quantum machine learning. I'll be giving a brief introduction about various algorithms, and we'll be having a short hands-on coding session on one of the recently developed algorithms in quantum optimization. The second session will be completely based around neural networks. We'll be seeing how we can use quantum nodes instead of just classical nodes in the conventional convoluted neural networks, and we'll be seeing how to code a program which uh, classifies between the MNIST dataset. I don't know if everyone is familiar with the image dataset. It's basically a dataset of handwritten images where you use neural networks to classify what images represent which numbers. So, without further ado, I would start. Uh, I'll tell you now. If you have any questions, feel free to unmute yourself and jump in with questions. I am always happy to field any doubts you might have. So, as you can see, the topic for today is overview of quantum optimization method.
Yes,
And
sir. The screen is visible, sir.
okay, okay. Okay. So as you can see, the overview, like today's topic is overview of quantum optimization methods and quantum machine learning. So this is my email ID. If after the session you come up with any doubts while thinking about the session, you can always email me. I'll be prompt in my reply. So what we'll cover today. First, we'll go over a generalized classification of what quantum machine learning algorithms will be. Now, this is not the kind of classification that most of you are familiar with. We will not be talking about supervised or unsupervised algorithms. Just keep in mind that any kind of classical machine learning classification that you might know of, it extends in the quantum case as well. What we'll be classifying are algorithms based on the type of your input data and the type of algorithm that we are employing. So for example, we have two types of input data. We have classical inputs and we have quantum inputs. Quantum inputs are mostly superpositions of various input states. And as for algorithms, if we use normal classical circuits to evaluate these algorithms, so they are classical algorithms. I am sure you are familiar with other the talks held prior to this. We showed you quantum circuits. So quantum algorithms use quantum circuits. Moving on, like I'll give you a high level introduction to five algorithms, optimization and machine learning algorithms. No, we'll not be going into detail over every single one. We'll be going into detail over two, but I'll be providing you adequate background so that you may conduct your own research from here on out. I'll also be providing you with tools to write your own codes. The third topic for the first session will be a hands-on coding session. We'll be applying this particular algorithm, QAOA. We'll be talking more about this to solve a very typical classical problem, the maximum matching problem in graphs. We'll be doing this coding on Python, and you'll see how easy it is to code such complicated algorithms on Python, even for quantum computers. So this will be the end of our first session. The second session will cover the following. We'll be explaining what we actually mean by having quantum nodes in neural networks. We'll be doing a recap of convolutional neural networks, and I'll be walking you through the layers. I'll be using PyTorch today to code the neural network. So I'll be walking you through the layers and be explaining like what we'll be referring to in the code. I'll give you an instruction on how to set up your own local environment for quantum machine learning. And finally, we'll have a hands-on coding session we'll be coding a hybrid quantum classical neural network to classify MNIST dataset. Uh, we'll be explaining more about this later on. Like for the time being, what we mean by hybrid quantum classical neural networks are our neural network will have both classical activation functions as well as quantum activation functions. So without further ado, we'll move into it. But first, before starting with classification of quantum machine learning algorithms, the first question we might ask ourselves is why do we need quantum machine learning algorithms? What's the use of having quantum machine learning algorithms? Because as we all know, deep learning is already at a stage where we cannot explain everything in detail. It's very complicated to actually map out how your neural network parses the data. We all know about how backpropagation mathematically works, about how feature maps work, but we actually don't know how to predict what kind of feature sets or what kind of weights we'll be needing for our neural networks. So why should we even complicate it further by introducing some kind of quantum flavor into this? The main reason, in my opinion, is as follows. Quantum mechanics, as we all know, is vastly different from classical mechanics. It has a different set of laws, it has a different set of axioms that govern it. But the main law that separates quantum mechanics from classical mechanics is reversible computation. So, reversible computation means any sequence of operations that you do will always have an inverse set of operations that lead you back to the original state. So basically, there is practically no loss in information, no loss in entropy. And if any of you are familiar with information theory, this is a huge deal. We can use this to show that any classical circuit can be efficiently converted into a reversible circuit, a quantum circuit. So the basic building blocks of quantum circuits are the AND, NOT, and OR gates. We can create these AND, NOT, and OR gates using our reversible quantum gates. And since we know how to create the building blocks, the universal circuits of the classical computation case in the quantum computation case, it follows that any circuit that you might make in classical computation, you can also do in quantum computation. So we can give out the theorem that quantum computing is at least as good as classical deterministic computing. However, this is a point which is very much misrepresented in mainstream media. We do not know if quantum computing is better than classical computing. Anyone who claims so is claiming it falsely. What we do know is whatever we can do in one case, we can do it in the other case. The main reason why we use quantum computing is that since it is based on quantum mechanics, we have access to the wave properties of particles, which helps us in some cases to demonstrate exponential speedups. But we do not know for sure if this is the general case for everything. Also, we do not know if classical computers can or cannot give those exponential speedups. So this is the quest for quantum supremacy, which basically says that if you can demonstrate that you can carry out a certain task on quantum computers, which cannot be efficiently done on classical computers, you are said to have achieved quantum supremacy. Now, the hands-on part, I'll show you the algorithm. So that algorithm has been proved theoretically to demonstrate quantum supremacy, but quantum supremacy is inherently a practical aspect. Quantum computers are very behind on the practical aspects. The hardware is very limited and it is extremely difficult for us to maintain coherent quantum bits. So this quest for quantum supremacy is still on. In some cases, it is disputed to have been resolved. We'll see this in today's lecture. So imagine the complexity class P. So this encompasses your efficient deterministic computation. Any Turing machine which runs in polynomial time and can solve tasks efficiently is in this complexity class. Then you have BPP, the bounded probabilistic polynomial time, which gives you randomized algorithms. And we conjecture that BPP and P are equivalent, but we haven't proved it yet. We have the quantum computing, the bounded quantum probabilistic time, polynomial time, which is thought to be a superset of BPP itself. But as in this case, we do not know if one is bigger than the other or not. It might be the case that everything is in the small p set, but we don't know for sure. What we know for sure is the BQP is at least bigger than P or BPP. Okay. So what do we mean by quantum machine learning? So this is what I was talking about earlier. So you can have two types of data or input, classical inputs and quantum inputs, and you can have two types of algorithms, classical algorithms and quantum algorithms. Now, in some cases, this classification matters a lot because in the yellow square that you see, whatever is has a quantum input and a quantum algorithm will obviously give you much better speed ups than what is in the pink square, which is the classical input and the classical algorithm. However, the problem is the input or the data that we have available to us in real life is classical, it's not quantum apart from certain cases. So when we try to convert the classical input into the quantum input for feeding it into the algorithm, a lot of our advantage is lost. This is something that which people don't see out loud, and this is misrepresented everywhere that I have seen so far. So this is something that you have to keep in mind. Just because theoretically it says that we have an advantage doesn't mean practically it translates practically. Okay. So classical inputs and classical algorithms are classical machine learning algorithms. So we all are aware of these support vector machines, normal neural networks, then linear regression, logistic regression, reinforcement learning. Anything that we know or are aware of so far are classical machine learning algorithms. What about quantum inputs and quantum algorithms? So we have quantum linear algebra simulations. So this is one of the core um, cores of quantum machine learning. If you have the system of equations ax equal to b, if you can solve that, then you can do a lot of operations. Even everything in classical machine learning is dependent on equation solving. So, and this quantum linear algebra simulation, this is theoretically giving us an exponential speed up, but as we will see, it does not always translate into that practically. So we also have quantum annealings. This is used for molecular dynamic simulations. We'll be looking into some of the techniques that are associated with quantum annealing. The reason for studying quantum annealing in a machine learning course is you can use some of the techniques that quantum annealing uses, namely quantum tunneling effects, to design optimization algorithms. So we'll go into this later on. We also have variational quantum eigensolvers, which is a pet project at Google right now. For the last 3 years, Google has been conducting experiments with this algorithm to show that there is some kind of quantum supremacy present. So however, the most important subdomain available to us right now are classical inputs and quantum algorithms. Note that when I say that I am talking about quantum algorithms, it means I'm talking about hybrid algorithms mostly. The entire algorithm will not be quantum since quantum circuits are very susceptible to noise. So we usually do some pre-processing of the parameters and hyperparameters in classical algorithms, and then we send in the parameterized circuits into the quantum algorithm, where it does the quantum stuff and returns our answer. So first is QAOA, which we will be talking about at length today. Then you have quantum neural networks, which we will also be talking about at length today. And we have quantum SVMs. So I'll not probably not get time to cover quantum SVMs, but like these are also we take the kernelization in the classical machine learning and we put it into the quantum Hilbert space. So to make it more simpler, in what we do in an SVM is you have two types of data and you draw a hyperplane to classify what type of data it is. So what happens when the data is very intermingled? We take the data and put it into higher dimensions so that we can find the hyperplane to separate the data. So what this is done very effectively in quantum since the quantum space is inherently higher dimensional than the classical space. So that is how we translate SVM into quantum SVM. But we'll probably not be able to cover quantum SVMs today. Okay, so moving on. The first topic, quantum linear algebra simulation. Let's go into a little bit of detail and see what it entails. So you have quantum linear systems of problems. Ax equal to b. So you have x are your equations, a are your coefficients of the equations, and b is your solution vector. So this, as we said, like this is a basis for all machine learning algorithms. If you consider x as your feature vectors, so solving feature vectors to get your predictions in B is the basis for machine learning predictions. So we have different algorithms for solving linear systems of equations classically. The fastest way to solve is conjugate gradient descent. People are aware of gradient descent, which takes like quadratic time. No, it takes 10 to the power 3. But conjugate gradient descent is actually the fastest classical algorithm to solve linear systems of problems. So it the time complexity is this. I'll explain the terms briefly, what they each mean. So n is the number of feature vectors or the equations that we are trying to solve. We have already assumed that it's a square matrix. If it's not, it's easy to rectify. We can just introduce dummy variables to make it square. S is the sparsity of the matrix. So in real life, say for example, you have a pixel. You have an image which is made up of pixels. So most often when we get the data to feed into into our neural networks or things like that, it has been cleaned. So most of the image is empty. It's black and white. So you have like edge sketching algorithms and stuff like that. So what I mean to say is most of the data in our input will be sparse. So S takes into account what the sparsity of the matrix is. The kappa is the singular value ratio. It's not very important right now. Epsilon is the error that we are aligned to incorporate into the algorithm. Now, in contrast with this, one of the simplest quantum algorithms to solve QLSPs is this, the HHL algorithm, which was given in 2009 by Harrow, Hasidim, and Lloyd. So as you can see, it has a logarithmic speed up, logarithmic factor on your input size, which basically means it is exponentially faster compared to the classical algorithm. But is this true? So I'll urge you to look at the two time complexities again. In the input size, it is logarithmically faster. It is exponentially faster. However, if you look carefully, it is exponentially slower in the terms of input and also quadratically worse in terms of complexity. However, in practical scenarios, your input images will be very large. So the other things won't really matter that much. And since we are using classical pre-processing to take care of the noise and everything, even the error doesn't matter that much. So in effect, it gives us an exponential speed up. However, the main problem with this algorithm is actually converting your classical input into the quantum input, because the HHL algorithm takes everything as a quantum input and gives you a quantum output. And the quantum output, when we measure it, it gives you, like, it collapses to one state. So in order to actually get the full picture, you have to measure it an exponential number of times. So it's not a very practical algorithm. However, there have been a lot of research on this topic, and there have been multiple new papers which have improved some of the other aspect of this, of the algorithm shown above. So this is something that you should definitely check out if you are into the theoretical side of machine learning and you would like to convert your algorithm into the quantum space. Any questions so far? Okay. So we return to our matrix. So now we take a look at the quantum annealing algorithm. So this is, you can think of this as your optimization landscape. You have the objective function which you are trying to minimize to the global minimum. However, there are local minimas along the way which might trap your gradient descent or batch gradient descent algorithms. So what we do in classical optimizers, and we use something called simulated annealing or hill climbing, where if we see that we are at the minima, we take the wrong path with some probability, which is called the hill climbing algorithm. So as you can see, in both, does anyone have a question? Yes. Okay. So we have this hill climbing algorithm where we take the wrong path with a certain amount of probability. Now the issue is that if the potential barriers are very high, it's not easy to get out of the local minimas. So higher the P, greater the difficulty. This is a saying in quantum annealing, in simulated annealing actually. So what do we do? Instead of doing thermal jumps or probabilistic jumps over the peaks, we use quantum mechanical properties to tunnel through. So your the thing that you have to understand is in classical mechanics, every object is a particle. But in quantum mechanics, every object has a wave function. Wave functions can pass through potential barriers, as in, I think you must be familiar with concepts of teleportation, which Tharma covered last time. So it's not as obtuse as that, it's a little more subtle. But the thing is, in the superposing state, you can have the wave travel through a potential barrier such that it exists in superposition on both sides of the barrier. And as you progress through time, it completely, yeah, yeah. Do you have a question? You're not audible. You can type in the chat if you have a question. Okay, like I'll carry on. Like if you have a question, you can type in the chat. Don't think like there's some problem with the mic. Yeah, so you can, as I was saying, you can tunnel through these potential barriers, which basically makes the height of the potential barrier irrelevant to our annealing problem. So the wave function can propagate through a potential barrier, and the height does not matter anymore. So like this is one of the unique ways in which you can take uh, so this is one of the unique ways in which you can take advantage of quantum mechanics over classical mechanics. We come to another type of algorithm called the variational quantum eigensolver. So this is one of the first algorithms that we'll see, which is a quantum classical hybrid algorithm. So how does it work? It has a quantum circuit which takes in quantum data and it processes the circuit, and we measure the circuit and we see what the uh, excuse me, can you mute that if you don't have a question? Yeah, so you measure the data and you get the parameters, and then you send the parameters to a classical optimizer, which in turn optimizes the parameters. So we are not sending the quantum circuit to optimize the parameters themselves. What we do is we perform the action, like the quantum computations on the quantum computer, but the classical pre-processing is done on the classical program. So this is a feedback loop, and we stop when we think that we have an output which has greater than or equal to the expected output that we require. And when I'm saying expected output, mostly I'm talking in terms of expectation mathematically. So so there are a lot of variations that you can do on these kind of circuits. Like it depends from algorithm to algorithm and problem to problem. But this is the general structure. So what happens with a quantum eigensolver? So similar to quantum annealing, which we claimed was used for molecular dynamics simulations, even VQA is used for quantum chemistry simulations. What we do is we train a quantum circuit to prepare the ground state of the input energy. So the Hamiltonian here is nothing but a physical description of the total energy of the system. It's like the kinetic energy and the potential energy and the other, like at the quantum level, you have other energies coming in, the nuclear energy and stuff like that. So the total energy of a system is physically described by Hamiltonian. So we prepare the circuit in the ground state, in the current state of the Hamiltonian, and then we evolve the circuit to finally get to the ground state of the Hamiltonian. So this is an entire process that happens. We'll see a graph next. So this is a graph of what happens in this VQA simulation. Initially, you see that we start at a very high energy level. So this is a graph of the Hartree-Fock simulation of hydrogen molecules. So we start initially at a very high energy, and then we eventually slow it down and finally settle upon the ground state energy, which is around zero point 0.8 Hartrees. So in this figure, you can see that the blue markers are actually done by classical Hartree-Fock simulation approximation. So the blue markers which try to approximate the curve, they are done classically. The red markers were done on Google Sycamore quantum computing chip, which is, as you can see, very surprisingly close to the actual exact energy. So, like as I said, Google's quantum computer Sycamore accurately simulated the released energy in 2016, and this was a huge deal. Like this experiment is probably the reason why there's so much interest in quantum nowadays. This and deep waves for quantum annealing experiments. So this was the experiment that put quantum computing on the map as a viable alternative for classical computing in the future. So this started the debate for quantum supremacy as it is. There are a lot more caveats to this experiment which I'll not be going into, but as you can imagine, not everything is what it seems. So IBM released a press release the day after Google published their experiments in Nature, pointing out the various flaws in methodologies and interpretations. But like we'll reserve that for the time being. The entire point is that even if Google did not achieve quantum supremacy in this experiment, it showed you how easily close we can get to modeling actual quantum systems using quantum computers. So this is something that you should definitely check out. If you are not interested in pursuing quantum computing or quantum machine learning, you should actually check out some of these topics that I point out so that like you can have something to ruminate on later. This is a very interesting thing that happened. So now we come to the quantum approximate optimization algorithm. So the QAOA algorithm was given as recently as 2014 by three researchers at MIT. Edward Farhi, Jeffrey Goldman, and Jeremy Goodman. So QAOA algorithm is also a hybrid algorithm, and there is a little mistake in the slide that it's not a mistake, it's a caveat. So the type of data is said to be classical, but QAOA also accepts quantum inputs. The note you have to make is for QAOA, the starting state that we have as in DQE. So we'll see this while we are coding up QAOA. It has to be efficiently preparable, otherwise all speed up is lost. So the QAOA circuit looks a little bit like this. If you take close look at the red and blue boxes, just take a look at the first two red and blue boxes. So what we do in QAOA, the quantum approximate optimization algorithm is we take a combinatorial problem, any combinatorial problem which has an objective function. So to put it in context for computer scientists and mathematicians, think about a linear program. It say a maximization program maximize C of Z subject to certain constraints. So the red boxes are responsible for encoding your objective function, and the blue boxes are responsible for encoding the constraints. Now, what they showed was that mathematically, if you keep on applying these layers one after another, if you keep on applying the red and the blue boxes one after another, and when it tends to infinity mathematically, no matter what the problem is, we can always find the optimal solution, which is a very bold statement. The problems might be NP hard, they might be NP complete, they might be sharply complete, doesn't matter. When the number of layers tend towards infinity, we can solve any problem that we want. However, as you might realize, this is not practical. Like nobody runs anything up to infinity. Certainly not a quantum circuit. Like there's too much noise and too many other variables going on. Then in 2016, they theoretically showed that whatever output you might get by putting in just one red box and one blue box cannot be simulated classically. Like this was a huge result. So QAOA, this algorithm is one of the forerunners for quantum supremacy. Now this theorem that was proved generally, and it has been 3 years since we are still, like I myself am also working on this algorithm. We are trying to apply these to various problems to see in which case the theorem actually holds, the quantum supremacy theorem holds. But nevertheless, it's a very exciting algorithm to work on. So after applying these P layers of the red and blue boxes, we measure and then we optimize the parameters. So the gamma and beta are the parameters to our algorithm. So we have rotation gates inside, and the rotation gates rotate by the angle gamma or beta, which is classically optimized, and then we update it again. So for example, like we'll be doing this problem actually in the hands-on. So take this graph, this pentagon. So it's a two regular graph, it's a cycle graph with 5 edges. Our we want to find the maximum matching in this graph. So a matching is nothing but a set of edges which have no common endpoints. So for example, you have M1 is a matching where E1 and E3 have no common endpoints, and also E2 and E4 have no common endpoints. So there are a lot more matchings possible. E1 and E4 have no common endpoints. So this is actually hard to do classically to enumerate all the matchings. Maximum matching is easy classically. You can do it in quadratic time. You can do it in quadratic time using flow algorithms. Yeah, so it's easy. But actually counting the total number of matchings present and enumerating all of them is actually hard. It's exponential since it can be as many as the total number of subsets of an edge. So it can be 2 to the power e. So this is actually difficult classically. It takes exponential time. However, we can do it easily as we will see now, like using the quantum algorithm. So After this, I will be starting the hands-on. I would like to stop here and ask you people if you have any questions. Any questions regarding? So we can go back and view all the slides again. So, so here we covered uh, whatever the session agenda will be. Why we use quantum computing? We theoretically like this is a theorem that any classical circuit can be efficiently quantum into converted in a quantum circuit, and it is as at least as good as classical computing. Then we saw in terms of complexity theory how it looks like. Then we saw the various types of algorithms that can be classified as quantum machine learning algorithms. So we have these. We had the QLSP where we solved the linear system of problems AX equal to B. We said that this was the fastest classical algorithm for solving these kind of problems, and then we showed that the quantum equivalent has an exponential speed up with respect to the input, and there are various more algorithms which are based on this algorithm. And we saw the quantum annealing problem, which is basically your optimization landscape in any machine learning problem. So instead of doing stochastic gradient descent or gradient descent and doing hill climbing, we do quantum tunneling to optimize. Then we saw VQE, and we saw an diagrammatic representation of the quantum classical hybrid algorithm. We said that this was an extremely important algorithm for modeling quantum chemistry problems. This was the output of the Google Sycamore experiment, which started the debate for quantum supremacy. And finally, we are on QAMA. So, like at this point, I would like you all to keep this diagram in mind when we are coding the problem up, because like this will help you understand what we are doing when we are doing. So, if there are no questions, then I will start. So before starting, like I had actually given these slides at the end of the neural network talk, but you will need Qiskit. So Qiskit is nothing but IBM's Python library. So there are a lot more. So you have Qiskit talk. So this is a Python library by IBM. I think the previous session introduced you all to Qiskit. So this is this page documentation slash install.html. Like you can easily install it on any operating system, any of the popular operating systems that you have. Even though it says Ubuntu, like I know for a fact it works on other Debian based systems. So and I'll be showing you all the computations on Windows. So yes, it also works on Windows. In fact, I would recommend Windows for a lot of reasons when you're working with quantum computing. But anyway, like you just install Anaconda, which is a package manager for Python, and then you install Qiskit in the package manager, and you are good to go. It's just 2 steps. Okay, so let's start. So first, what we do is this is my Anaconda shell. So first, what we do is we activate a new environment. So I have already created this environment in advance. So what you can do is like you can just create conda, create some new environment, and you can do pip install Qiskit. It's as simple as that. So in my system, it will already show that it's already installed, so that won't be a problem. So it installs and it will say that Qiskit has been installed. So now Qiskit is installed. So what we do is now we open up a Jupyter notebook and we get to coding. So this is my Jupyter notebook. So I'll open up a new Python 3 notebook. Let's name it UAA FDP. Rename. So first, to test if Qiskit has been installed or not, we just import Qiskit and see if it has been installed. So the first load takes a little bit of time. Yeah, so it ran without any issues. So I'm guessing it has been installed. Good. So now let's start doing the. So first we need to import a few libraries. So the libraries will be from Qiskit. We'll import uh, the quantum circuit library. So these three, they execute AIR and the IBMQ libraries. These are needed for our backend simulation. So we'll be using the AIR library of Qiskit to run our quantum code on a simulator. So we'll not be using actual quantum backends for this, since like it's going to take a lot of time to show you how to set that up. I'll be just running it on local quantum simulator. But I think that should be proof of like enough for a proof of concept run. So Qiskit dot tools dot Jupyter import star from Qiskit dot visualization import star. So these are, so the Jupyter, this you won't need for your, like if you're running it on a Python script, but this you will need for plotting histograms and drawing the circuits and everything. So now next you have, we'll import some math libraries. We'll import random. We'll also import NumPy, and we'll be importing math and how would we need math? Okay, if we need math, we'll import math. So classical register, it cannot import name classical register from Qiskit. So okay, so let's run this again. I think because we imported Qiskit. Okay. Oh, this is the problem with Jupyter. Yeah, so it's now imported. Okay. So now we'll start coding up the circuit for the diagram. So before we start coding up, like I'll like you to see the diagram once again. So you had two alternating layers, and what we are supplying as input to the alternating layers are the edges of the graph, so that we can form matchings on the graph. So that is what we will be coding up here. So we'll be creating create circuit. We'll be taking as input the edge list of the graph. We'll be taking as input the number of phases or the number of times we want to apply the red box and the blue box. I'll be calling them red box and blue box, but they have their own names. So which I'll be writing out. They are called the phase separation unitary and the mixing unitary. So the number of times we'll be applying these phase separation unitaries to the circuit. And then we'll be taking in a list of two lists of parameters, the gamma list and the beta list. So first things first, we declare our quantum registers or the qubits. So these are the qubits that, so again for example, like the S1 to Sn, these are all qubits. So these are what we will be referring to as Q in our circuit. So Q are the S1 to Sn. Since we have E edges, so we'll be putting in E. Number of quantum registers at E. So to measure these quantum registers, we'll need E numbers of classical registers to take the values of these quantum registers. We'll also need some ancilla qubits. So ancilla qubits will be our workspaces. We'll just need one ancilla qubit for this experiment. So that is done, and now we create a quantum circuit. So QC is equal to quantum circuit Q comma C comma ancilla. So here we have our, so this is the quantum circuit that we'll be using for Q here. Now we define the terms for our quantum circuits, like what the actual gates and operations will be inside the circuit. So as we know, there are p layers in this circuit, and this gamma list and beta list are each p arguments long. So for k in range p, we'll be extracting the pth argument. So k refers to the phase that you are in. So gamma is equal to gamma list k. Similarly, beta for this layer is beta list k. So we have extracted the argument for our current. Now we'll be doing the red box. And the red box is just a one-line operator. Red box or the phase separation unitary. So this is just a one-line operation. We'll just be applying a Z rotation gate, which basically manipulates the phases on your qubit. So the higher the matching size is, the more your phase will be on that qubit. Like, this is a very gross oversimplification of what I'm doing, but the math behind it is a little bit involved. So I'll be skipping over that. But like, this is the phase separation unitary for our circuit. So if anyone is interested in the actual math behind it, I can refer you to some papers that you might like to check out. So you can contact me after we are done. So QC dot RZ. RZ is a Z rotation gate, gamma Q. So what this does is, if we apply the Z rotation gate to the qth qubit, to all the qubits like in our circuit with the gamma operator. Now we are done with this. Now just to make the circuit diagram a little bit better, when we'll be drawing the circuit diagram, I'll just put in a barrier over here. Like, it will look nice. So for I in now starts our blue box or the mixing unitary or the constraints. So here is the objective function. So how do we go about the constraint? So just before coding it up, just let's take a look at this graph. So excuse me. So what we said earlier was that these edges must not have any common endpoints. So in order to do that, we must make sure that whatever like edges are already present in our matching, those do not get disturbed by new edges coming in. So you'll see what that means. So for I in range length of E. So since E is a list, we are taking the length of the list, which is basically nothing but the number of edges, and we are defining a controls array. So this controls array will be taking each edge and seeing what edges are adjacent to this controls array. So for j in range length of p if j equals I, then we continue. So if the edge is already present, then we don't need to do anything. So if it is the same in the outer and inner loops, so else if now we do the conditions. So E over here that we are entering, I should have said that earlier. So E will be in the form of a list. So it will be like for the triangle graph you have three edges 0, 1, 1, 2, and 2, 0. So this is an easy way to input the graph. This is the edge list representation of a graph. So when we are trying to see which controls are applicable, we will just check the two endpoints of the edge list. So what we do is if ej0 equal to ei0 or, so we have to repeat this condition 4 times for each of the I'll explain why we are repeating this 4 times. So if you see this earlier, so 0 is our I and 1 is our j. So if this edge has 0 in it, that means this edge is also a control. Similarly, if this edge has a 1 in it, then any edge that has a 1 in it, the vertex 1 in it, will also be adjacent to that edge. So basically, we are checking the adjacencies in this graph. So ej1 equal to ei0 or ej0 equal to ei1 or ej1 equal to ei1. So the four cases that we have. If then we put this as a control, controls.append, we are putting the jth qubit as a control of the ith qubit. So controls.append qj. Cool. Now what do we do? Now we try applying the control operations on this ith qubit. So qc.x on controls. So if any of these edges are already present in the matching, then we turn them into 0. And if they are not present in the matching, then we turn them into 1. The entire algorithm is if all my controls are not present in the matching, so they'll all be 1, then I will be able to evaluate whether every control is not present in the matching. If and only if none of the adjacent edges are in the matching, then I can include the ith qubit in the matching or the ith edge in the matching. So qc.mx or mcx, so we take all the controls and we hand them into the ancilla qubit. So if any of them, so let me put this in writing here, say if the jth qubit is a neighbor of the ith qubit and is already 1, then qc.x will make it 0. Okay, so my num lock is off. Will make it 0. So if it makes it 0, then my multi-controlled x will evaluate equal to 0 if any one neighbor is 0. So I hope this makes it a little bit clear. So if any of the neighbors are 0, then this ancilla qubit will be set to 0. If the ancilla qubit is set to 0, then we'll not be including this the current edge in the matching at all. So now comes the process. How do we include the current edge? We do it quantumly. We create a superposition between two states. Either we include it in the matching or we don't include it in the matching, but with associated probabilities. So what is the operation for that? We just do a controlled rotation, a controlled X rotation with the beta parameters. This is our red box parameter that we have. So controlled rotation beta from ancilla to the ith qubit, and we are done. So we just, what do we need to do? We just need to reset all the qubits. So qc dot reset ancilla. We reset the ancilla to whatever state it was, and we also reset the control bits since they might be acted on after this controls. And we are done. Let me check once. Yeah, I think we are done with this. So now all we have to do is return the quantum circuit. Oh yeah, we are done. Yeah, this is one of the reasons I don't like coding on Jupyter. It doesn't provide an ID. Yeah. So let's see if I have written the code correctly or if there are any typos. Yeah, it compiled. So this is the quantum circuit that we'll be using. So once again, like again, another refresher, you can check the red box and the blue box are applied one after another with different parameters. We have done nothing but just do that same thing over here. So now we come to the this part, the green part. So we have to measure and calculate the counts or the probabilities of the output state. So let's measure. Let's define, write a function for measuring. So we can actually do this without writing a function, but I want to show you multiple instances of what happens when we are having just one layer or three layers or different graphs. So I'm just writing the results. So define get result. So this quantum circuit that we are outputting from the create circuit class, we will be passing this as an argument in the get result class. The number of qubits. So we need number of qubits we need to measure. So number of qubits equals number of qubits. We overload the function in the variables. We define the number of shots that we have to take. So what do I mean by the number of shots? So this is the number of times we'll be running the circuit for a given input on the quantum backend. Since quantum circuits are probabilistic in nature, you cannot just run them once. You have to run them for a certain number of times for the probabilities to settle. Since we are doing the simulations, so if you just run it once, whatever input you get will have one probability. But we cannot have that. That's not a realistic sample size. So increase the population. So shots is the population which denotes the number of times we are running the circuit on the backend. So now that we have defined the shots, we will define what the backend is going to be. So backend will be the air library that we imported here. So air dot get backend QSM simulator. I think Tharma might have showed you all this, but like just in case I'll show this to you again. So on the actual quantumcomputing.ibm.com, so you have multiple simulators. So these are all actual backends that are running. So this is the reason I'm not using the backend since they're almost always full. So if you have 1 hour to run it on, then fine, go for it. We don't have time right now, so I'll do it on the simulator. But and like for example, this Armong simulator is free, but it has just one qubit. It doesn't make sense to run matching problem on a graph with just one edge. So Yeah, we'll probably need something like 6 qubits over here, given by, yeah. So if we want to run it for a 5 edge graph, so this is something that you can use, and there are a lot of tutorials which show you how to access this, how to run this from your code. So how to run this from your code is this IBMQ library that you have. You use that to get a provider. So you have an API token over here. So I am not clicking that. I don't want to show you my token. So you have a token over here. You use that token to access the API, and using the API, you can use any backend that you want. So instead of writing QSM simulator here, if you have the right token, you can write IBMQ Vigo as given here, IBMQ Valencia, whatever you like. So backend equal to AI.get backend QSM simulator. Now we must tell our function what to do. So we'll measure. So we'll measure range length of E. So the first argument is the number of qubits that we are measuring starting from the first qubit, and the second argument is which classical bits are we measuring it to. So we don't have any such compulsions. We are measuring across the range. We are just not measuring the ancilla. So length of QE. Hopefully the measurement is done. Now all we have to do is we simulate this measurement. So equal to execute QC. We execute our quantum circuit along with the measurement on the backend for the defined number of shots. Shots equal to shots. So we have defined the backend, we have defined the shots. So now what we do is counts is equal to QAOA dot get results. QAOA, simulate. Oh, we need to take the simulate dot result. Simulate dot result. So this gives you a dictionary. So QAOA result this. So we take the dictionary and we print it out. So I might have made some typos here and there, but we'll see if it doesn't run. So we return the counts. We return the counts. So let's see. Yeah, I made a typo. Oh, in the last one. So this is our get result, and now we are finally ready to actually run our experiment. So let's copy this, whatever we had, this triangle graph, and let's run it for p equal to 1. And let's define the gamma list equal to any random parameter, like a random np.random.rand p. So we have p random numbers over here. We have beta list is equal to again the same thing, and we create a quantum circuit. So we'll check the definition again. What was the definition? So we create a circuit with E, P, gamma list and beta list. So we'll copy this, and we have everything as required in the definition. So and what we so result equal to get result. Now that we have made the quantum circuit, we'll just QC comma length of the A. So there are some errors here. Register size must be castable. So the range of oh, so what I did was that I passed the entire thing into combine these qubit arguments, controls MCX, and I'm appending C dot control. Okay. So there seems to be a problem in the ending part. So whatever we are applying, whatever the controls are, we are applying the controls, we are appending the controls to that. We are applying the MCX gates, the multi-control gates. And so for what happens if I put this is still it is running somewhat, so we'll debug that part a little bit later. I just wanted to show you. So print results. Result. So it just gives you one output. So if we run it again, we'll get, yeah. So this is the problem. So the MCX gate is required for the ancilla. Oh, acha. Okay. And length one, it's one. Now you see that your output dictionary has a lot of like phases and all, but it's not actually clear what these mean. So what we'll do is before we explain what output dictionary means, I'll just plot them for you. So we'll plot the histogram of this results. We'll plot. So this plot histogram function is coming from this visualization dot import this Qiskit visualization import dot star. So it has the plot histogram and a lot of other say state vector plots and block spheres plots. It has a lot of plotting functions that you can use. This is the easiest to understand. So you see that we have already achieved some kind of a result even with random parameters. So what we are seeing here is that the matching which has only the first edge. So in a triangle graph, all matchings are either of zero size or one size. So you see that we can generate all possible matchings here. So the first edge is 001. So this is something that we were looking forward to and we got it. So if I change the parameters and the results, like if I run the circuit again, it will give me a different probability distribution and so on. So there seems to be an issue here. Control got append QA. So maybe we can just remove this part. So we can just run it again. Yeah. So as you see, if we run it multiple times, it will give you different results. So let's run it on something a little bit larger. So instead of E is equal to just 3 edges. We'll do it for the graph that we saw earlier. So let's run it on 5 edges. So it will be 0, 1, 1, 2, 2, 3, 3, 4, and 4, 0. So 3, 4, and 4, 0. Okay, one more arguments is empty. So x dot controls is empty. So there is some problem with this operator. Let's try to debug what this problem is. So what we want here to happen is if the jth qubit, so why is this empty? So let's print. Print J. So it's J0, J1, J0. Okay, so it's going into the loop. Very nice. So we are just not being able to append it. So and QG. So let's put in QG and see what happens. Okay, so print QG. This should work. So one of the arguments is empty. Okay. So we have 0, 1, 1, 2, 3. If P is equal to length of P, of Q. So let's did anyone say anything? Okay, well, hopefully like when we come back for the second session, I'll be able to rectify this, but hopefully you have an idea of what is supposed to happen for this one. So let's go back to the previous. Let's try to see what the problem is. So histogram result. Something else that you might like want to see is what happens if I change it from random inputs to something that I know will work. Input P and from beta list equals to 3.0 into P. 3.57. Let's give it pi np dot. Okay, instead of that, let's do np dot pi. So what happens? So print results. So we just get the one result. So this is a parameter that I knew what would work. So this is how we actually do it. So how do I go from this random input to this? It's actually very easy. You can just feed it into an Adam optimizer or any classical optimizing loop that you have. It will do the plain gradient descent. So this part of the algorithm is classical. So we start with the random inputs and we end up with the proper inputs. So in case we wanted to find a maximum matching on something, this is what we have. So I hope this made some sense to you. I'll try to correct this part in the second half when we get back, like why this part is not working. But apart from that, any questions from anyone? So any kind of questions regarding the code part or regarding any of the other algorithms that we saw earlier, anything that you have. So, like, let's go through this once. Like, what we did was that we created a circuit with two types of boxes. The red box. Oh, yeah. So one thing I can show. So, suppose we want to see what the circuit looks like. So, we can just draw the circuit in a lot of ways. So, this shows you what the circuit looks like. So, oh, I think I know what the issue is already. Yeah. So you have XXX and it goes just from 1 to 1. Here just so the controls are not being. So as you can see, you have two layers. The first layer separated by the barrier is your RZ gates, which is the red box, and the entire layer after that till we start measuring are the mixing unitaries that you have. So this is a cool trick that you can use to see what circuit you're drawing. You can also like draw it in ASCII if you want, ASCII or text, which is I think the default option. Yeah. So this is the default option if you want to see what parameters you have. Say we didn't go with this. So we just kept the random inputs. So we plotted the histogram results and we plotted this. So now you can see what the inputs were. It was 0.139 radians for the gamma part and 0.57136 for the beta part. So this looks cool. What happens if we do it for more than one round? So we can go for 2 rounds or 3 rounds. Let's go for 3 rounds. So you can see it goes for 3 rounds now. We print the results. Let's see the histogram. Now we see that we are converging towards that 1, 0, 1. We have created superposition over all subsets of edges here, and we are converging towards the maximum matching that we think is correct. So the circuit now will be considerably longer. It will span 2 or 3 rows. Yeah, it will span through 2 or 3 rows. Something interesting that you might take away from this is, so as you can see in the output, we have a superposition over all subsets of edges. However, if you see the code complexity, it just runs in n square or p square. It just goes over all the edges that you have. Okay, I got the problem. No, did not get the problem. Okay, whatever. So it is P into E square, the circuit complexity, which is polynomial. However, you see that you can actually generate an exponential number of subsets just using the quantum part. So this in itself should seem wonderful to you that we are using polynomial depth circuits to create superpositions with non-negative amplitudes over all possible circuits. So this is something that you might look to incorporate in your own problems or in your own programs. Like this is the power that quantum computing gives you. And this entire power comes from actually this one line. It comes from this one line. This line produces superpositions between edges which are in or not in the matching. So yeah, I think that's all I wanted to show everyone for QAOA. So we can rerun this circuit again. We get a very large circuit, but this circuit is still polynomial with respect to the input. So doubts, comments, questions, anything. So, so Bhavya, should we break for the next session? Like since nobody seems to be having any questions.
Yes, sir. Let's have a break for 15 minutes, sir.
Yeah, like so I'll be online during the break. So if anyone has any questions, like you can ask, or like and so if anyone wants to send mail right away regarding questions you have, so you have my email ID on the screen. So, okay, so let's break and then we'll.
Dear participants, if you have any queries, please you
Yeah.
can raise in the chat box or you can unping and ask to sir. Let's have a break for 15 minutes. Thank you all.
So when we come back, we'll be looking at neural.
Uh, we'll be come back at 3:40, sir.
Okay, we'll come back at 3:40 and we'll be looking at neural networks then.
Okay, sir. Okay, sir. Thank you, sir.
Okay, sure.
Sir. Hello.
Yeah, should we start?
Yes, sir. Shall we start, sir?
Okay.
Okay, sir.
Yeah, so continuing where we left off, like I made a small mistake in eliminating this part, this what is actually necessary. So, like if it's the same edge, then we don't check it, we skip it. So now what we get as the output for the QA algorithm will be something like this. So this is actually what we get. These are so previously we were getting all the subsets of edges, like all possible subsets of edges. Now we get all possible matchings in the graph, which is actually more useful. Uh, which is actually more useful in our case. So, so we are. I ran this for p equal to one. We can run it for p equal to one and see what happens. So even in p equal to one for random arguments, we have this distribution, and for the arguments that we know which work best, if we give it as input, so we get one maximum matching as the complete output. So I did not want to leave this as a loose thread in our discussion. So if you want, I can share the code with you later on. So this is how the circuit should look like in the case of p equal to one. So the first before the barrier, the first layer is the red box, and the later layer is the completely it's the mixing unitary or the blue box. And for when we have it for p equal to 3, which is not necessary since for this graph you can already see it. So okay, so we can do one thing for this graph. We can increase it to what 4 edges and see a square graph. See what happens. It still gives the correct answer. So in that case, like the number of gates increase actually. So this is something that would have bothered me if I left it alone, but okay. So let's close the QA discussion and move on to the neural network discussion now. Okay, so leave. So we were the neural network discussion. Now for the second half, we'll exclusively concentrate on the neural network discussion. We'll be talking mostly about like quantum nodes in neural networks. So this is a diagrammatic representation which is given by Penny Lane. It's a platform distributed by the company Xanadu. So I'll show you what. So Xanadu.ai, they are a company which who specialize in quantum machine learning as such. So and they have different architectures. Out of the possible different architectures like IBM's Qiskit, Google Search, they use superconducting circuits like Josephson circuits. Xanadu uses photonic hardware for Strawberry Fields platform. Similarly, you have PennyLane. PennyLane is an open source for quantum machine learning, computing, quantum chemistry. The interesting thing about PennyLane is it's kind of plug and play. You can write code in PennyLane and run it on any of the popular backgrounds that you have, like quantum computing backends. So you can run it on the Qiskit backend, the code that we were writing earlier. You can even run it on Rigetti's Forest backend or Google Circ or Amazon's Bracket, which is hosted on AWS. So this is a very, you should check this out if you actually want to do quantum machine learning hardcore, or you might stick to Qiskit. So for today, whatever code we'll be writing, we'll be sticking to Qiskit because like that's what you have been introduced to so far. And Penny and all, they are not that popular, but this is actually easier to start coding on than Qiskit. So this is something that I wanted to get out of the way. So the way the Penniman architecture or the neural network architecture is set up is you have a neural network consisting of quantum and classical nodes. So what do we mean by nodes here? Nodes are the perceptrons in the neural network. So they have inputs, weighted inputs, and they have a function inside them which calculates the expectation or the probability or whatever you want basically inside the function, and they give an output. So you can substitute the classical circuits inside the classical nodes by quantum circuits, and you get quantum nodes. The main challenge with having quantum nodes, so the yellow boxes here represent quantum nodes. Main challenge with quantum nodes is it's not clear how to do back propagation in quantum nodes. And back propagation is the crux of neural networks. That is how the neural network learns from its mistakes. So you have loss functions, and then you use the chain rule to back propagate throughout the, but this is not clear how to do it in quantum nodes. So I'll be talking about how we do kind of a gradient optimization or a backpropagation in neural network in quantum nodes today. And I'll be assuming that everyone here knows or has an idea of basic neural networks and how backpropagation works. Like I'll not be going into details of the chain rule and backpropagation. It's just calculus, like it's the chain rule of derivatives at its very core. So we will talk about quantum classical neural networks now. So this is the structure of an artificial neural network. As I was saying, weights are updated in classical nodes using backpropagation. But what about quantum nodes? So quantum nodes are like this. So as we saw earlier, so allow me to skip back a little bit before we come back to this. So even in the QA part, you saw that the input to the quantum circuits were parameters, the theta and gamma, the gamma and beta angles that we were supplying. So this is also apparent when you look at the code that we wrote for um, so the code that we wrote for our QA program. So what we take as inputs are mostly the parameters are the angles that we use for our unitaries. So this is something that you should keep in mind. So they need not necessarily be angles, but our quantum circuit will always interpret these as angles. Now, why am I saying angles? Angles are basically since they're reversible operations, what they do is they rotate a vector around the origin by a certain angle. So whatever input you give into a quantum circuit, it will interpret it as an angle and perform the corresponding rotations. So we must take advantage of this property of quantum networks for in order to emulate back propagation. So as you see in this circuit, you have an angle theta that goes into the quantum circuit, and you have an output f of theta. So f of theta, I wrote here that the output is the expectation value of a measurement observable, which basically means like you measure a qubit and whatever you get, it need not be the expectation always. It might be just the probabilities, or it might be some other higher order moments of the angle. But in any case, like you can interpret these as expectation values of the observable. So our objective here is to calculate the gradient of f of theta and then feed it back into the loop to minimize the losses. So the output can be formally written as a parameterized quantum function. So this quantum gradient is the vector of partial derivatives of the quantum function. So mathematically, what does it look like? It looks somewhat like this. You just take the partial derivative over the different components of the quantum vector. But the problem is this is actually very hard to evaluate. Why is this hard to evaluate? A quantum bit has an exponentially more number of components compared to a classical bit. So a 2-qubit system has 4 dimensions, while a 2-bit system has 2 dimensions. So if you wanted to calculate this gradient efficiently, you cannot do it classically. Like you cannot, first of all, you have to measure it exponential number of times, then you have to like perform the partial derivatives exponential number of times. So this is not an efficient classical way of doing things. So this is hard to calculate. So what do we do? We do this. So we the can express the partial derivative as a linear combination of other quantum functions. And the special thing about these other quantum functions are they are based on the same circuit but with different parameters. So it looks somewhat like this. So f of theta basically says what happens when theta is applied to the circuit in the picture. So f of theta 1 and f of theta 2 are the same circuit but with different parameters. And the best part about this is the angles are classical, like they can be macroscopic angles. So they can be something like pi by 4 or pi by 3. They need not be infinitesimally small angles that we have no idea of dealing with. So this is called the parameter shift rule, which actually makes it viable for us to use quantum neural networks. So these quantum functions use the same circuit but different parameters. So I'll stop at this point and ask you if you have any questions because like this is going to be critical moving forward. So if anyone has any doubts about this, you can ask me. So to recap up to this point, I know we did not cover a lot, but still like to recap up to this point, each of the gray perceptrons here are classical. What we do is after seeing the output, we check whether the prediction matches with the target labels. If they do not, we calculate the loss or the error and we back propagate it through the through the neural network. But this is not done efficiently classically for quantum nodes. So what do we do in quantum nodes? Like if we had to do it classically, I showed you we cannot do it classically since it would take an exponential amount of time to calculate in the first place. So what we do is we use the parameter shift rule with same circuit but different parameters, and this allows us to calculate the gradient for this function. So theta 1 and theta 2 are actually related to theta in that they are shifted by a certain angle. So say theta 1 equal to theta plus pi by 3 and theta 2 equal to theta minus pi by 3. So something like that. So you have your original input parameter and you perturb it by certain angles to even get different parameters. So I hope you have a high level understanding of how we will be calculating the back propagation on quantum nodes. So now we'll review convolutional neural networks for a bit because we'll be coding a CNN from scratch for MNIST dataset. So like it would do us good to understand what's going on instead of just seeing what's written on the screen. So in a convolutional neural network, you have multiple layers with different functionalities. So say suppose you have this input image of an X. So you can take this image and break it down into different pixels like grayscale values or pixels. So these are normalized values like so 1 minus 1 values what you have on screen. So you take this X and you apply different filters on the X. Now, how do we know what filters to apply? This is something that is part of the learning process of the neural network. So you run it enough times so it understands what kind of kernels or what kind of features it needs to extract. Initially, our task is to just define the size of our features or kernels and let the program run. It will eventually formulate a good kernel for us to evaluate the uh, input image on. So the input image is referred to as a channel on PyTorch. Like we'll be using PyTorch for the neural network thing. So this is called an input channel. We have one input channel since there is one picture. And after applying three kernels or three feature extractions, we are left with three output channels. So most probably like we will be using six output channels for the first layer, then 12 for the second layer and so on and so forth. But like this will give an idea of what I'm writing when I'm doing the coding. So and then as I said, like we don't know what's in the kernel, we just define the kernel size. So in our case it's a 3 by 3 filter, so we make the kernel size as 3. So this is a convolutional layer. We input an image and it comes out to be a stack of filtered images. So on the screen you have very like interesting features that I would like to point out for curiosity's sake. So an X is consisting of three parts: the left diagonal, the right diagonal, and the middle part. So so those are the three features that we see on the screen. Okay. Now we come to the normalization layer. So it's hard to deal with negative values for any kind of systems. So what we do is we remove the negative values or we normalize the entire range of pixels into a preset range, say from 0 to 1 or from 0.5 to 1 or whatever you like. So we'll be using the ReLU normalization, the rectified linear unit. So it works like this. So any negative values are mapped to 0 and positive values remain like it's a linear function for the positive values. The interesting thing is ReLU is a non-linear function, so it can be mathematically shown that using enough ReLU layers you can approximate any function you like. Okay. The third kind of major layers are the pooling layers. Using the pooling layers, we reduce the stack size of the images. So it's not viable for us to deal with huge images throughout the length of the neural network because as we said earlier during the HHL algorithm, most of the data is anyway sparse. Like for the X we saw earlier, you just have useful information in a fraction of the cells. The rest of the cells are just background. So it's not entirely necessary for us to keep the entire image. What we can do is like we can consolidate the values, we can aggregate the values into smaller sized images. So they use filterings and there are a lot of techniques for pooling. Like you can do an average of kernel window or the maximum value of the kernel window and so on and so forth. I'll not be going into details, but like to recap, you have the convolution layer, which is a stack of filtered images. Normalization layer normalizes the values, and the pooling layer reduces the size of the stacks. So now what we do is we apply these layers in like multiple times. So each time we keep on applying convolution layers, we create more and more features and we then normalize them and then we pool them to reduce the size. So by the end, you can see this 28, like this 1, 2, 3, 4, 5, 6, 7, 8, 9. This 9 into 9 image has been filtered to 3, 2 into 2 feature factors. So this is somewhat manageable. Now we take the output, the final output of this entire deep stacking. Oh, and this is where the term deep comes from. Like we stack the layers to make the network deep. So but the backpropagation thing remains the same as it was in neural networks. So we take this and then we say that every layer gets a vote. So this is a fully connected layer. Now here also at this step there are multiple ways of taking these feature vectors, like this is called flattening this process. You take these 2D matrices and flatten them into a 1D array. Now there are multiple ways of uh, you classifying based on this flattened 1D array. Like the most popular ones, which everyone will have heard of, are softmax classifiers. Then you have the binary cross entropy classifiers. These are also like very closely related to loss functions as well. So we take them and then we say if it is an x or a zero, we so these are all weighted functions and we feed them into the classifier which says it's an x or a zero. And then we have this. Bhavya, I think people are asking for some kind of links. Okay, so the thing is that in this case, what we do is we don't use the normal conventional for our neural network that we'll be doing. We won't use the normal conventional new like classifiers that we have. We'll be using a quantum classifier instead, and that's going to be the fun part. So putting it all together, we have this structure. So if anyone has any questions, you can type in the chat or unmute and ask up to this point.
Sir?
So, yeah, I think someone has a question.
Hello?
Yeah, yeah.
Sir, generally when I take an image, I convert that image into an array. Then
Yeah.
I apply one kernel on the particular image, whether it might be horizontal kernel, vertical kernel, any kind of one kernel. So
Yes.
then automatically the image is been synced, right? For example, if I take 10 cross 10 image, then if I apply a kernel on a particular image, then automatically the image is been resized. Then I'm
No.
going to lose.
Yeah, yeah. So it need not necessarily be resized to the length that you want. So it depends on the type of resizing that you're doing. So sometimes what we do is we take the input image and then we expand the margins according to the kernels. So say suppose we are applying a 3
I
cross,
mean strides.
huh?
I mean we call it as a strides.
Yeah, yeah, just try. Like I did not want to go into that much detail on this. So there are techniques which actually need the resizing to the pooling layer. Like of course, it's not a very big deal if you combine the pooling layer and the convolutional layer into
No, no,
one.
no, sir. Before pooling only, for example, if there is an image 10 by 10, if
Yeah,
I
yeah,
if I apply a
it
filter
reduces.
on a 4
Uh,
cross 4 filter, embedded
yeah,
filter,
yeah, it
then
reduces.
automatically the image is n minus f plus 1 by 2 is the formula that we will going to
Yeah,
use.
yeah.
Then automatically the original image is being resized. Then in that scenario, I'm going to lose some information from the particular image. Then how to handle these things in
So,
this?
so the thing is that it's you cannot think of it as losing information. Uh, So how to put this in a better way? So when you are doing the kernel, when you are applying the kernel, what you are doing is a process called feature extraction, right?
Yes, yes, yes.
So you don't have like you don't take the initial image and then you apply kernel and get one particular image. So you have the initial image and you apply as many features as you want. You do as many feature extractions as you want. So one image becomes
No, no,
10.
no. I will be not applying only one filter. I will be applying 64 filter or
Yeah,
12850. It depends upon
yeah,
me. Then
yeah.
automatically
So you
for
are
each
not
filter,
losing information, you are gaining information about that particular kernel. So you have to think about it in this way.
yeah, I agree with you. Why? Because we are getting the dominant pixel. For example, if there are
Yeah,
ones in the particular pixel, I'm using whether it might be horizontal kernel or vertical kernel or diagonal kernel. So
yeah,
according to that kernel size and kernel property, then automatically I'm extracting those properties. In that
yeah.
scenario, there might be noise. But I think that there
Oh,
might
okay. Yeah,
be
yeah.
delay or noise.
Yeah, yeah. So I won't be dealing with that right now. Like that's a topic for like hardcore machine learning talks. But yeah, it is possible that there might be noise, and that is why actually so these classic CNNs like we don't use these classical CNNs anymore, right? You have new types of deep learning networks that have come up like
Yeah.
that basically deal with these kind of issues. So
Yes. Yes.
and like when we are talking about this, like let's talk about some other things. So we are just talking about images, right? In this case, static images. So
Yeah.
You can have sound signals, you can have videos, which are
Yes,
more
yes.
susceptible to noise. So yeah, that is a very pertinent issue in this. And I there is one implicit assumption that I am running throughout these two sessions is there is no noise. This might seem funny, but if there is noise, then the classical noise is the least of your worries right now, because whatever I showed for the quantum part, like that is heavily susceptible to noise. So for the time being, we are working with an idealistic world. Ki whatever we are doing is correct. Okay.
Yes.
Yeah, but it's a great question. Like that's a great query. Like so, harping back to the initial point that I made about this quantum versus classical thing. So this loss of information is the main reason why people are actually looking into quantum computing.
Sir, sorry to interrupt you. Generally, due to the property of decoherence in these kind of concepts, we are going to see more kind of error in these qubits. Or,
No, no, I am not talking about decoherence and noise due to error. I am talking about information loss.
yeah.
So
For example, if there is an image, if the image is corrected, then automatically information is
no,
lost from the image, right? Then we can claim it as a
assume a noiseless channel in this case. So this is under the noiseless conditions.
okay.
So when you have classical circuits acting on that, even in noiseless channels, you are susceptible to information loss. Say and circuits.
Okay, okay. I got you. I got you.
Yeah, yeah.
Yes, sir.
So that is one of the foremost research areas that is going on in quantum right now is quantum error correction. So if we
Yeah,
can
fine.
come up with good error correcting techniques for quantum computing, like, and this is different from the error by noise. So error correction is about the information loss that is happening due to noise. Decoherence is physical error, like the atoms are not staying in place for
Yeah,
long, they are
yeah.
losing energy.
Entanglement.
Yeah, entanglement, like atoms are getting entangled with like the atmosphere itself, like it's a very big pain right
Yes.
now. So like this is a huge area, this quantum error correction thing, classical error correction thing. So
Yes.
for I should have mentioned this before. Thank you for asking this question actually. Like this was a very good question. So
Yes.
we are currently assuming that there is no noise, which is not realistic, but it is what it is. Like otherwise I won't be able to fit it into 1 hour.
Yes, sir. Yes. I
Yeah.
thought to ask this question, but due to as you are continuing your session, so instead of if I disturb something, then the flow will be disturbed. So I
No,
thought to ask at least.
sure. Like this was a good question. Like so actually like for everybody listening, this question that he asked was very nice in a way. This actually brings up a lot of questions about the articles that you see on mainstream media. Like why? So people are hyping up quantum computing and people are hyping up machine learning and stuff. And as like, is your name Funny? So as Funny pointed out, like this error thing is a huge deal in both machine learning and in both quantum. And the even interesting part is since we actually don't know what is going on in the deep learning structure, since this is a learned structure, we actually don't have any proper ways of dealing with this error. So people have switched away from this model into newer models, like they are switching away to different models. But yeah, like this is a discussion, this is a huge discussion for another day. Like if you want, you can mail me, we can talk about this later. Okay, any other questions? Uh, so I don't think there are any other questions. Okay. So was that like do you have any other questions? Funny?
Yeah, man, sir.
Yeah, do you have,
Yes, yes. One last question, sir.
yeah, 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 please.
Sir, yeah, in deep learning, with respect to classical computing or quantum computing, the concept is same, right? There will be neurons, and the weights is been generated by algorithm. Then automatically input plus weight is been transferred to the other neuron. Activation
Yeah,
function is applied on the particular neuron. So
yeah.
generally, we use optimizers to calculate the loss and to back propagate the loss. I mean, to reduce the loss, we use optimizers.
Yeah.
So when the same optimizers are being implemented in the quantum computing or in this quantum kind of
Yeah.
algorithms,
Like
like
we showed that the quantum annealing algorithm that I showed. So that
yes.
can be used as an effective replacement for gradient descent and all. But then you have to take into account for practical purposes the cost of employing such algorithms or such hardware is very high.
But in deep learning, I use GPUs, sir. I will render a GPU and I will perform my task. But in
Yeah.
quantum, we
So
can't. Even though if I render a GPU, it won't sufficient for my computationally.
so you will use a GPU to do what? Quantum optimizing.
No. I am not familiar with quantum, sir. I am familiar with
Okay.
only deep learning. So for deep learning, I will render a GPU from the cloud and I perform my task. But if I want to perform these things, if I want to perform these things by using quantum, how do I'm getting somewhat.
Okay. So how to do this? So you saw previously in the code that I wrote. Were you there for the earlier session?
Sir, yes, sir.
Yeah. Is the code visible now on the computer?
Yes.
Yeah. So this line that we have, this backend, what we are
Okay.
assigning. So this backend is actually going and running on actual quantum computers. So for in this case, I am running it in a simulator since I needed to do it fast for everyone to see. So what happens is that when you are doing your calculations on a CPU based system or a GPU based system, it's happening locally. Instead
Yes.
of that, we are sending the jobs to, okay, since you asked this question, I think instead of going into too much theory, this should actually help satisfy a lot of. Uh, so I'll show you a few jobs that I have been running for my research and stuff.
Okay,
So,
sir.
uh, this is the IBM Q experience. I think your earlier
Yeah,
session.
yeah, yeah. I've
Yeah,
gone through this, sir.
yeah. So this result, so this job that I have run before. So this is a job that I sent from my system to run on the quantum backend.
Okay, fine.
So this is where the so you see so this is where the quantum backend actually works. So you have a transpiler, you have a quantum assembler. So did you look at QSM codes and stuff like that?
No, sir.
Okay,
Not yet.
I'll show that also a little bit.
Okay,
So you see you have a backend which is called the IBM Q Santiago. This is based in Brazil right now.
okay, fine.
I sent the job, whatever optimizing I had to do for my quantum codes, I sent the job to the actual backend, it went there, it ran, it gave me a probabilistic measure, and it returned this circuit.
Circuit. Okay, yeah.
Yeah. And the interesting thing is, so whatever circuit that we are seeing here, these circuits are actually high level gates. So these
Yes.
circuits are not what actually happens on a quantum computer. You use U gates, which are basically photonic gates. You alter the state of the photons. So
Yes.
U gates are basically these gates that are happening over here. So these gates, as you notice, these are very different from what gates we have been using in our system.
Yes.
Yeah, and this is actually the same circuit, like the same kind of circuit that you have.
Okay,
And
sir.
this U gate thing, you can like so this is what happens on the actual quantum computer, the gate progression, and you can have the assembly code for this, which is very different from the high level code that we are writing. So this
Okay.
is the high level code that we wrote. The
Yes.
circuit dot apply this thing. The assembly code is a little bit different. So in essence, what you are asking, things happen the exact same way on a CPU or a GPU or a quantum computer, is
Hmm.
just the underlying architectures are different. That's all.
Okay, fine. Yeah,
So,
I got
so
it.
yeah. So I am not a physicist. I am a computer scientist by profession. Okay.
Okay, sir.
So even I don't have a very deep knowledge of what actually happens in a quantum computer. Like today, if you put me in a room with a quantum computer, I won't be able to program the quantum computer to run something. But I know the high level concept. Like so, we computer scientists are good at abstraction, encapsulation.
Yes.
So we treat this entire thing as a black box. I run the code, I have my backend, my job goes to the backend, it runs. But this is very interesting field, but it's not a field that computer scientists can get easily into. So you require a lot of physics background for
Yeah,
this.
quantum
Yeah,
physics.
quantum mechanics. Yeah, so you will need this. But glad that you asked. Like, so there is a lot of free knowledge and resources out there. Like, if you're actually interested, so you can see like in the last month I ran a lot of jobs, and every one of them went and ran on some of the other system over here. Yeah.
Okay, okay.
So that's a good question. And like, so when we are trying to optimize instead of using say classical optimizers like Adam optimizers or Kobila optimizers, we'll just go and run it on this quantum annealing system that I showed you for the, so this um, yeah, this quantum annealing system. So instead of navigating the entire landscape, the optimization landscape using classical computers, we use quantum computers to violate the potential barriers.
Okay, sir. Yes, I got.
Yeah,
Yeah.
okay.
Thank you, sir.
Very nice questions. Thank you. So, anyone else have any questions? Like, so, okay, if you don't have any questions, then like we can do an interesting thing. So I don't think I'll have time to code the entire neural network by hand, but I already have some codes written. I can walk you through the codes, run them, and show you how they work. Instead, what I can do is like I can show you how to set it up for yourself, so that you might try doing this on your own. So the first thing that so this every connected layer gets a vote, and what we were saying is that on this level, this is where our quantum circuit. Uh, I Lokeshwari, like I am not aware of any attendance link, so you can contact your administrator if you want, like the organizers, if you want. So okay. So this is the part where the software classifiers come into play or anything else comes into play. This is the part where we use our quantum layers, the quantum circuit for determining what happens. So putting it all together, we get a CNN which gives you these values. On an X, it's a 0.92, on a 0, it's a 0.51. So we pick the higher value, we go with 0.92. So we have successfully identified our input image as an X. And like this is something that like can help you relate to what was happening. So instead of using it as a classifier layer, we can also use it as kernels. So how do we use it as kernels? Each and every single pixel is like applied to each and every single pixel like is applied to certain quantum operations, and you can have similar feature outputs as as shown on the figure.
Excuse me, sir.
Yeah,
Sir, can I have one more question?
yeah, sure.
Can you go to the previous slide, sir?
Yeah, yeah.
Sir, there you have written fully connected layer 2 times. So how do you come to know for this problem statement only two fully connected layers can be
So this
solved?
is like kind of ad hoc in some senses. So this is not exactly a very scientific process, as you might say. Like we might require one fully connected, we might require two fully connected.
Generally, we go for hyperparameter tuning. I mean, tuning the algorithm.
Yeah. You can do all that. Like I am not going into details of how it might work or not work. Like you can obviously replace this as like with any permutation you like. It's
Yes.
nothing is a necessity for
Okay.
in this case.
Okay.
Right? You can
Okay.
play around with various permutations of classifiers, error corrections, and you can play around with tunings, like hyperparameter tunings, parameter tunings, anything you like. This
Okay.
is
Fine.
something that we like. I use somewhat. Okay.
Okay. Yes. Yes. Thank you.
Okay. Yeah. No problem. So, so before we get into this, so earlier I just started running the code willy nilly. So now I will introduce like all the setup. So previous session you might have seen how to do it on IBM Q website, like this website, which um, um, so you can run quantum codes on the quantum lab. You have Jupyter notebooks on the quantum lab and stuff. But for heavy duty tasks, I would actually tell you from personal experience, doing it online is not a solution. You have to set up your own system, like own local system. There might be like huge delays in getting jobs back, or in general, like Jupyter notebooks are not as powerful as Python scripts themselves. So there is a lot of codependency on the underlying platform when you are doing it online. So you can easily access all the backends using APIs from your backend. So I think it's better if you knew how to set it up on your own. So the first thing that you need to do to set up a quantum machine learning system or a quantum computing system is Anaconda. You need to install Anaconda. So if you are familiar with this, very nice. If you are not, like this is a package manager for Python on Windows. Like you can have it for Linux and Mac, but it's most useful on Windows because Windows you don't have the sudo, you don't have the apt-get thing installed. So Anaconda serves as a good package manager. So to install Anaconda, go to products, go to individual edition, and you download. You so you download for Windows whatever like word size you have, 64-bit or 32-bit. You download it and get it running. So you have so once you download it, you have two things. You have the GUI, which looks. I'll see if I have the GUI installed. Anaconda. Yeah, you have the Anaconda Navigator. This is a GUI which I never use because like it's a little bit cumbersome to use, but it comes along with nice IDEs. Like you have integrated development environments. Like you don't make the same mistakes that I made while typing out. And the other thing that you can have is the Anaconda prompt or the Anaconda shell that we have. So the GUI is loading. I don't even know if it is installed or not. I have never installed worked on it. So this is the Anaconda shell. It's just like your command line shell, and this is yeah, it's starting. I walk you through the GUI. Okay. So after you have installed Anaconda to run quantum computing, what you need to do is you need to install Qiskit. So file new notebook Python 3, let's say, starting a new notebook. So the first command that you need to give, so this you should type on your command line, but like I'll type it on. So when you're typing into the command line, ignore the exclamation mark. So pip install Qiskit and your Qiskit will start running. So it will install and Qiskit contains every package related to quantum computing that we have. When you're done with Qiskit for machine learning purposes, and you can go to the website of PyTorch or TensorFlow. I would prefer PyTorch because like it runs a little faster on my system. I have no GPU, so every computation that I do is like CPU bound. So PyTorch seems to run a little faster, but I have worked with TensorFlow also. Yeah. So as you can see, this is the first time I have started run the GUI, so it is showing.
But PyTorch is somewhat complex than TensorFlow. According to me, I worked on TensorFlow. In TensorFlow, we are having a Keras wrapper. So
Yeah, you have okay, like you even for this thing you have like non-CUDA applications. This is a matter of personal choice actually.
CUDA is nothing but it's a NVIDIA kind of
Yeah. So I don't have NVIDIA graphics card. Like I have AMD graphics card. So anyway, like I cannot use CUDA. So there is no boost to my GPU.
yes.
Yeah, so that is why like there is if so this is a warning for everyone out there. So if you are buying a laptop or you're setting up a desktop for machine learning purposes only, be sure to check if you have NVIDIA graphics or not, because most of the graphics acceleration is done by this library called CUDA, which is incompatible with other kinds of graphics cards like AMD and others. So if you don't have NVIDIA, you'll have to use your CPU, which I am doing for these days. So if you're doing it for like small projects at home, it won't matter that much. But if you're doing it for large projects, it will actually make a difference. So, but then again, you won't be doing large projects on your computer. You'll be hooking up to your institute's high performance computer. But yeah, like that's a warning that you should have. So I don't think I'll update Python now. You can check this later. So PyTorch is a library, Python library for machine learning. So it's not just a Python library, it works on C++ and Java also. So installing PyTorch is easy. You just go to pytorch.org, click on get started, and you just click whatever combination you like. So say suppose I want the stable build on Windows and I want to install via pip for Python and I don't have any CUDA. So I click on none. So this is my installation command. I take this and I run it on the command line and it installs. That's it. As simple as that. So you have set up PyTorch, you have set up Qiskit, and now you are ready to run machine learning
Sir,
algorithms.
sir,
Yeah.
even TensorFlow, there is a GPU version and CPU version, sir. So
Yeah,
what?
yeah, TensorFlow, there is a GPU version and CPU version. It's a matter of choice, preference, what you use.
No, no. As a learner, if you according, so even I worked for deep learning kind of
Yeah, yeah.
basic knowledge I'm having. So according to me, I choose Py rather than PyTorch TensorFlow. Why? Because there I am having a wrapper called Keras. So by using sequential layer, it will be easy for me to establish the connection, neural connection.
Okay,
But
so I will show you how you can do it on PyTorch. Like I will be walking you through the code. It's actually very easy in PyTorch also. So this preference boils down to which of these layers you first use. So
yes, yes,
whatever library you first use, you can do that. So for everyone who is listening to this lecture, so there are whole host of nice tutorials out there on PyTorch or on TensorFlow. So anything that you wish to start working on, you can start working on. I personally prefer PyTorch. You can work on TensorFlow if you like. So okay, so now that we have installed everything, now let me show you the Conda cheat sheet once. So yeah, so this is the graphical. Uh, so this is the GUI layout for Anaconda. So you can start Jupyter Notebook, you can start your prompt, you can start a IPython console, and Jupyter actually. So Anaconda works for any of your programs. So Python, then MATLAB, R, anything you can use. Even the same goes for Jupyter. So Julia, yeah, Jupyter's first two letters stands for Julia. So these are tools that you need in order. So you have RStudio also installed by default. So this is the first time I am seeing the navigator. So this is your GUI. You don't need to be worried if there is only a command line shell for working. It's very beginner friendly. So yeah, I want to quit. So now we go into, so we let's restart this. So let's close this down and let's restart the kernel once. So I'll show you step by step how we work. So I open the Anaconda prompt and say I want to go into a directory that I already have. So I already have written the code for this quantum neural network thing. So in this code, in this folder, FDP presentation, FDP code. So I go into this code. Now you have multiple environments that you can set up in Anaconda. So a way to create an environment is like this: Conda create -n new Python equal to 3.7. So my so yeah. So this is how you create a new Python 3.7 environment in Conda. So similarly, you can do this for R or for MATLAB or anything that you like. So now it will set up this new environment. Yeah, I will proceed with this installation. So it downloads and extracts packages. This takes a little while, like it will install all these things. So once you have finished setting up a new environment, you can activate that new environment and start coding on that. The takeaway from this is like in any at any point of time, if you require different environments for different builds, say in one kind of environment you need a NumPy 13.3, in another kind of environment you require an earlier version of NumPy. So you can have different environments set up for your needs. So we see that we have installed this. So conda activate new, and we are into. So this first bracket shows us that we are now inside the new environment. Okay. So we won't be using this new environment. I have already installed everything. So here you can install PyTorch and Qiskit and everything. So if you install Qiskit, it will take a lot of time. So what I will do is I will go into this environment that I've already prepared before, which was FDP environment. So contact with FDP. So now I want to, before I start going into the coding part, I want to check what all I have installed. So that I can do the packages list, I can see by typing conda list. So it shows me what all packages I have installed inside this FDP environment. So you see a lot of packages have been installed. So let's check the important ones first. So we have AutoGrad installed, which is somewhat a NumPy type package for PyTorch. You have NumPy installed. Yeah, you have NumPy installed 1.9.3. This is actually an earlier version of NumPy. The latest version does not work with PyTorch. So then you have PennyLane, and also I had installed everything for this. So you have PennyLane, you have Qiskit, you have all the Qiskit libraries installed, and PyTorch. So it must be somewhere here. PyLatex. Torch. Okay. So yeah. So you have Torch installed here. So you have all the PyTorch libraries installed here. Torch Vision, Torch. So this is an easy way of checking whatever packages you have installed for this current environment. So if I go back to the new environment that I had, if I do a list on that, you will not see any of these packages present. Only these packages are present. So now I go into this Jupyter notebook, and now I'll start the Jupyter notebook where I have the code written for you all. So this is the Jupyter notebook where I have the code written. So this is my notebook for the quantum neural network part. So I'll walk you through whatever definitions that we have here, and hopefully that will be useful for you to understand. So the first cell is our import libraries, what you have. Next, we declare a quantum circuit class. So this quantum circuit class, objects of this class will be used in our neural network layers. So what do we declare in the quantum circuit class? We declare that it's a Qiskit quantum circuit, and we say that it is initialized by the number of qubits that we require and the backend on which it is going to run. So the backend can either be your local simulator or your quantum computing backend that is on the cloud, say IBM's or Rigetti's or PennyLane's. So then we declare the theta variable, which is the parameter which we supply, and then we set up a small circuit. We apply Hadamard's to all qubits, and we apply the Y rotation gates to all qubits based on the theta parameter. So that's it. So this theta parameter is obtained from the library that we have for Qiskit. You can check the documentation. Qiskit is actually very well documented. That's one of the upsides. So what do we do when we run the circuit? So when we run the circuit, as you remember what we did in the QAY case, we execute the circuit by passing the backend and specifying the number of shots. And this parameter binds is a little extra thing for binding the command line parameters to the specific qubits. We won't be making much use of it. So as we saw earlier, we get the dictionary from the result, the dictionary of counts, whatever shots translated to which state. We store this in the result array, result dictionary, and then we convert it into this counts array and the states array. So in the QAI case, the states array were the strings signifying the matchings, and the counts were the number of times our backend simulated those strings. So then we compute the probability by dividing the counts by the total number of shots, and we calculate the expectation using like the states and the probability, and we return this. So in our case, when we apply this quantum circuit to the classifying layer, the outputs will be expectations of the input layers. So whatever input we give, the output will be the expected value of that input when passed via this Hadamard and the RY gate. Next, we declare the hybrid function. So this is the hybrid quantum classical function, which basically tells the neural network how to deal with the forward and backward methodologies. So we already covered that backpropagation is a little bit different in quantum nodes. So forward nodes is easy, like this is standard PyTorch definition. So this shift parameter is actually going to be used for our backward nodes. So I should pull that slide out again. So the shift parameter is actually what goes into theta 1 and theta 2. Theta 1 equal to theta plus shift, theta 2 equal to theta minus shift. So the shift parameter goes into that, and then we declare the backward propagation method. So what happens in the backward propagation method? We define the shift right and we define the shift left. So this is basically we are masking the current context shift with some array of ones, and then we calculate the right expectation and the left expectation. So the right expectation is the value of f theta 1, left expectation is value of f theta 2, and then what we do is we take the difference of these two. So basically what we are doing here, so the gradient of the original function is the difference of these two. So the gradient is the difference of these two tensors, and then we append this gradient to the already existing gradients. And this is how you do the back propagation for quantum nodes in neural networks. So now the last class that we have, no, not the last class, this is the second last class that we declare. This is the hybrid class. So the hybrid class actually takes the hybrid function and makes a convolutional layer out of the hybrid of the function. So you see that this class returns the hybrid function run on itself on the parameters that are supplied. So let's start running the codes. Otherwise, you won't be able to understand what's happening. So these are our definitions up to now. So 1, 2, 3. Now we move ahead. We have still not defined what the neural network structure will be like, but now we start extracting the data, the trained data and the test data. So we extract the trained data using like this is very common code you can find anywhere. So we take from the data sets, the PyTorch data set that you have, Torch Vision data sets, and we extract the MNIST data set. and then we only take the labels of 0 and 1. So MNIST has label like images from 0 to 9, but we are only sticking to 0 and 1 to better fit with our analogy of x and 0. So we have a train loader. So we load these extracted data sets and now we show the samples. So this is what the samples look like. So this is a training data set. Similarly, we do the same thing for test data set, but we don't show the samples because that is what we are going to find out now. So we are training on 100 samples, but we will be running the test on 50 samples. So now we define the neural network class. So this is the most important class and I'll be walking you through every line of this. So just a moment. Yeah, my voice was becoming hoarse. So first we declare the initial convolutional layer. So look at this. So here you have the number of input channels as 1, the number of output channels as 6, and the kernel size to be 5, and this is specifying the output of the first convolutional layer to be a 2D matrix. So this is a convolutional 2D. So let's look at what that means in terms of the figure that we saw before. Yeah. So we have one input channel in this, the first convolutional layer. We have three output channels in this, and the kernel size is 3. So contrast that with the code that we are writing. We have an input picture, an input image, and we train 6 features on it. So we don't know what the features are. This is a hyperparameter, but we assign 6 features to it. The neural network will do its magic of backpropagation and find out the best features possible. And the kernel size is 5 instead of that small 3 that we were using. So it's a 5 cross 5 feature map now. So then we declare the second convolutional layer, which takes in 6 feature maps like before, but gives out 16 feature maps. So now you can think about this as the second layer taking in the three output channels and then giving out 4 features for each of them. So they become 12. So similarly for our layer, we take in 6 and we give out 16. So now we come to the dropout layer. This I did not explain in the previous slide. So what the dropout layer does is it basically randomly drops some features. This process is not entirely random because it's motivated by the final value a feature has on the output. But for our purposes, we don't actually understand how the model is being trained. So we consider this a random dropout process. So even the dropout gives you nothing but it drops some features and leaves the rest as it is. So this linear, now we come to the linear layers. So these linear layers are the fully connected layers that I was talking about in this diagram. So now we declare the linear layers. So what happens in the linear layers are we take in this 256 1D array, 256 size 1D array. So where does this 256 come from? So this 256 comes from this. So the output of the second convolutional layer will be 16 and each image is of size 4 cross 4. So this gives you 256. So the input to this first layer, first fully connected layer will be a 256 1D array and the output will be 64 1D array. And the FC2, the second fully connected layer, will reduce it from 64 to just 1. So it will give you 1 or 0. So the feature map will tell you 1 or 0. And finally, we declare our quantum hybrid network, which will act as the classifier. So it takes in the backend QSM simulator, which we have been using so far. we have 100 shots and the shift parameter is pi by 2. So whatever parameter that I decide on, the left will be theta plus pi by 2 and the right will be theta minus pi by 2. So this is what the classifier layer looks like. So now we actually start making the neural network. So this can be actually broken up into two statements, like you can have x equal to self dot on which is the first convolutional network x, and then you have the x equal to f dot relu x. So the first statement can be replaced by these two statements, and we have already seen what they mean. This is the convolutional layer and this is the normalization layer. And after that, you have the max pooling layer, the pooling layer. And after the pooling layer, we again have the second convolutional and second normalization layer. And then we again have another pooling layer. And then we have some dropouts. After the dropouts, we again normalize. So this view and normalize is internal functions for the neural network themselves. And then finally, like we have the last two fully connected layers. And after the fully connected layers, we are going to apply our classifier, our quantum classifier. And what we return is a prediction on whether it is 1 or 0 at this point. Okay, so let's compile this. So this ran without any issues. Now we start training the model. So we take this neural network that we have defined and we train this as a model. We take the loss of function to be the negative log likelihood loss, which actually works well with quantum classifiers. You have Covilla optimizers which work well with quantum optimizers. You have Adam optimizers and you have quantum gradient descent. So this is up to you to play around with. Like this is what I use for this tutorial. Like you can use it anything that you like. The world is your oyster. We train for 20 epochs and we start training. So it will slowly start calculating the minimizing. Yeah. So now we see that it's 5% done with its training, 10% done, and every step it tries to reduce the loss. This will take some time. So if I had a CUDA system, it would have run very fast in 10 seconds. I have a CPU based system, so it takes a little bit of time. So this will train up to 90%. Yeah, and like this is another reason why when you are buying a laptop, you should get something that supports CUDA if you're doing for machine learning. So we are almost done. The loss has been optimized. That's good enough. Okay, so yeah, I think it's done. So now we plot the loss. So this is like the training convergence. So as we said earlier, we are using the negative log likelihood loss, which is this NLL loss, and we are comparing it to the training iterations. And as we can see in front of you, like they went down almost monotonically. So it did not go down exactly like that, but close enough. So now that we have finished doing this, all that's left to do is run our trained model. So we have trained on the training data. Now all we have left to do is we want to run this on the test data. So we declare the loss function. Yeah. So this is what we get. So, oh, this is nice. I was not getting this earlier. So we got 100% accuracy on our test data. So let's run it a few more times and see if it changes. Nice. You guys are lucky. So we get a loss of 0 minus 0.98 and an accuracy of 100%. That's great. So you might say you don't believe me. So even I don't believe it. So let's plot and see. So these samples were from the administrators. Yeah, it looks like it has predicted everything successfully. So this is how you incorporate quantum nodes into classical networks. And keep in mind that the most important part was left to the quantum part, the classifiers. So it seems like we have achieved our objective, and I don't have anything else to show you right now. So questions. So, yeah, I'm done. Okay, questions.
Dear participants, if you have any queries, please you can ask sir or you can type in the chat box.
Yeah. Okay, so if you wanted to, like, I'll be sending the slides to Bhavya, like, she can share it with everyone. So, and if you wanted to contact me, so my email ID is let me share first slide. So, so you can find my email ID on this slide. And you can even go to my website and check out my CV or anything else you require. And if anyone is interested in working, like doing research, or do you have any practical problems that you would like to apply to with quantum machine learning, you can approach me. Like I am almost always available.
Hello sir.
Yeah.
Sir, thank you for accepting our invitation and delivering
Welcome.
a nice presentation, sir.
Thank you.
It's really hands-on. It's really very nice, sir.
Yeah, like so the issue is that with the hands-on, it's actually difficult to do it over online. Like I was not sure about my net situation at home. So like
Okay, sir.
this would be a better experience in person, I think, like these kind of seminars.
Okay, sir. I will share your contact details with the
Yeah, yeah, please,
participants, sir.
please
If
do. And
anybody,
please,
if anybody interested in to contact you, they can contact you, sir.
okay. And
Sir,
like, I'll send you these slides, like you can share them with anyone who participated.
okay, sir. I will share the slides, sir.
Okay.
Okay, sir. If you
Okay.
can send the slides, I will share the slides to the participants, sir.
Okay.
Thank
Thank
you,
you.
sir. Thank you
Thank
so
you.
much, sir.